So good day. We are the third group. I'll introduce some examples of the hidden Markov model. So let's start from a very simple example. It's adapted from Wikipedia. So imagine you have a girlfriend. You meet her every night. When you meet her, she kiss you or beat you or do nothing. So what she do depends on she's feeling during the daytime. But you do not know how is she feeling during the daytime because you cannot meet her in the daytime. So every night you meet her and he do something. And you would like to get the answer. So how is she feeling during the daytime? Happy or unhappy? So we built a hidden Markov model for this example. Because you do not know how's she feeling, happy or unhappy. So it's hidden state. But she kiss you or beat you or do nothing when you meet her. So you can know this information. It's observations. So what we are going to do is using the hidden information, using the observation to inform the hidden states. So your girlfriend has some parameters. So the first day, she have the probability of 0.6 happy and probability of 0.4 unhappy. And during the following days, she's happy or unhappy depending on the previous day. So if she's happy in the previous day, she will be happy of the probability of 0.7 and unhappy in the probability of 0.3 and similar as unhappy. So this is the transition probability. And if she is happy, she has the probability of 0.5 kiss you and probability of 0.4 beat you and 0.1 probability do nothing and similar the unhappy. So this is the emission probability. So now you have met your girlfriend in the continuous 3 days. In the first day, she kissed you. The second day, she beat you. The third day, she did nothing. So how is she during the 3 days? Happy or unhappy? We will using a dynamic programming algorithm called the what-be algorithm to get the answer. I think we are already familiar with it. In the first day, in the first day, the probability is 0.6. She's happy, and if she's happy, the probability is 0.5. She kisses you, and so the probability of she's happy in the first day and kiss you at the first night is 0.3. And similar, the unhappy status. So during the second day, during the second night, she beats you. So if she's happy in the first day, she has a probability of 0.7, still happy in the second day. And if she's happy in the second day, the probability she beats you is 0.4. And so she's happy in the first day and kiss you in the first night, and happy in the second day and beat you in the second night, the probability should be 0.084. And the other three situations should be similar. And we get the higher probability. The 0.084 is higher than the 0.027. So we get this path, and also this path for the unhappy status, and similar for the third day. So now the highest probability is we get this path. So it's most likely she is happy in the first day, and unhappy and still happy in the second day, and do not happy in the third day. So we use the hidden Markov model to solve this question. So now let's talk about the DNA sequence. So imagine the 5' splice site recognition problem. So assume we are given a DNA sequence that begins with an exon, contains one 5' splice site, and ends in the intron. So we are going to identify where the exon switch to the intron. So the information we can get is based on the sequence statistics of bases. So for every base pair, it may have three hidden states. It may be exon 5' splice site and intron. We do not know the hidden state. We can only know the observation is AT, AC, G, or T. So now we have the start probability of 100% to start at exon. And this is a transition probability. So if one base pair is exon, the following base pair have 0.9 probability still exon, and 0.1 probability to become the 5' splice site, and similar the 5' splice site and intron. So this is the transition probability. And the emission probability is based on the base pair compensation differences between the exon 5' splice site and intron. So we assume in the exon, all base pairs have equal frequencies, and the 5' splice site, it always be G. And the intron should be AT rich. And then, so this is a hidden Markov model. And then we solve the problem using the just talked dynamic programming algorithm. And we find the most likely is this path. So it has the highest log probability, and have the 5' splice site here. So then we talk about gene finding. We will start with very simple, very simplified model. So it only consider about the coding region. For every base pair, it may have 9 hidden states. The first base pair of the start codon, the second base pair and the third base pair of start codon, and the first, second, and the third base pair of the common codon, and also the stop codon. And the observation are also A, C, T, G. The transition probability is, so we know if the first base pair is the first base of the start codon, so the next base pair must be the second base pair of start codon, and so on. And what we do not know is when the base pair is the third base pair of codon, so it may be returned to the first base pair of codon, or go to the stop codon. So we also get the transmission probability based on the different base pair compensation on the first, second, and third position of a codon, and also on the start and stop codon. So now this is a simplified codon region hidden Markov model. It's very simple to add some states. We add one state of intergenic base pair, and 8 states before the start codon, and 3 base pairs following the start codon, and also 3 base pair before the stop codon, and 8 base pair after the stop codon. So it became the more complex hidden Markov model. It fits the prekaryotic unspliced gene. So for these, so for every base pair, it may have the 9, not 9, so many hidden states. But the observation is still the 4 base pair, A, C, G, T. And the transition probability and the emission probability we do not show here. It's also based on the DNA sequence statistics. So if we add some more status, it became the eukaryotic gene hidden Markov model. So at the first line, so we now look at the first line. So because there are introns, so if the introns start just behind, just after the third base pair of codon, is the first line. If the introns start after first base pair of codon, is the second line. And this is the coding region. So the start codon should be here. It enters the codon region, and it may have 3 passes to enter the introns, and then go back to the exons. And when the model in the exons, there are some probabilities to the stop codon. Then we just add some more status of the several status for promoter and several status for the 5' UTR, and also several status for the 3' UTR and poly A and the intergenic region. We will get the normal eukaryotic gene model. So having this model, we can predict genes in a sequence of anonymous DNA. So, so then we also just talked the dynamic programming algorithm. We go through the hidden Markov chain. When the model, when the chain goes through promoter states, a promoter was detected. When the chain goes through start codon states, the start codon was detected, and so on. So, so it's obviously there are so many possible variations of the model. So we can add more states as we need. Maybe the model cannot detect every DNA all correct, but it may detect DNA fit this model. So I've finished. Thank you very much.